Welcome to the topic of parallel bound rendering. Today I'm going to focus on the parallel image compositing problem for parallel bound rendering. So remember last time we talked about there are two different strategies for parallel bound rendering. One is divide the screen into different tiles and have each processor responsible for casting ray from the pixel within its own tile. However, we mentioned that this method is difficult to scale up because each processor will require the entire dataset to handle images from different views. A more scalable method is to perform parallel by data. Essentially, we divide the data into small chunks and then assign each chunk to a processor which will be responsible for generating small images created from that chunk. As you can see that this will produce many small images, or we call partial images, from subdomain of the data. In order to produce one single final output, we need to composite the images together. So this is the problem of parallel image compositing. It is used to composite or blend all the partial images together generated from the subdomain. Just like many other parallel algorithms, the important goal for designing an efficient image compositing algorithm is to minimize communication. What are the communication? The communication is caused by the need to send and receive images among the processor that generate partial images. We want to minimize it, that is, we want to send and receive less data. The other goal is to balance computation, that is, we want to avoid having a small set of processors doing all the blending work. We want to make everybody equally busy as we are putting all those partial images together. One special issue for this parallel image compositing problem is that when we blend the partial images together, we need to follow the visibility order. That is, as we are generating a sequence of partial images, as the example here from A to H, we have to follow the visibility order. That is, we are going to blend A over B over C over D and so on and so forth all the way to the image in the back, that is H. This dependency of the computational task make the parallel image compositing a little bit tricky. So here I can give you a more formal problem statement. Assuming you have a sequence of partial images from A to H along this visibility order, how are you going to parallelize this computation? One solution is that you can divide the sequence of a compositing into many subpieces. For example, you can perform A over B, that is, blend A and B together using one processor. And then you can blend C and D together using another processor. These two processors can perform the blending in parallel and then blend the partial result again. In the example here, I break the A to H image compositing into 4 subsegments, that is 4 pairs. This requires 4 processors. And after that, I get partial result of A and B blended together, C and D blend together, E and F blend together, and G and H blend together. Then I follow the order of the visibility, then blend result of AB over the result of CD to get ABCD. This will require one processor. Similarly, I will blend the result from EF over the result of GH, and this will require another processor. After this stage, I got 2 partial images that I have blended. Then I blend all those 2 together, which require one processor to get final result, that is A, B, C, D, E, F, G, H. So this is actually one implementation of a parallel image compositing. In the first stage, I use 4 processors to get 4 partially blended results. In the second stage, I use 2 processors. And in the final stage, I use 1 processor. And I need 3 stages, which is logarithmic of the number of images, that is 8. And that's the number of stages I will need to perform this parallel image compositing. Let's perform some simple analysis. First of all, the algorithm I just presented required a total of log n stages, where n is the number of partial images in the beginning. And this is because at every stage, we are going to reduce the number of images to half. How many images are we going to communicate in total? In the first stage, I'm going to require to send 2 to the power of log n minus 1 images. So why this is the case, just imagine our example of A images, because we divide the A image into 4 groups. And within the 4 groups, one processor is going to send the image to the other processor that was 1 image. So the total in the first stage, we are going to send 2 to the power log of n minus 1 images. That's half of the total partial images in the beginning. Then at every stage, we are going to reduce the number of images that need to be communicated to half. So from 2 to the power log n minus 1, we're going to add half of it and half of it. And in the end, we have 4 images, 2 images, and 1 image all together. If you add all those numbers together, you're going to realize that the total is n minus 1 images. This is how much data we need to communicate. About parallel efficiency, you probably can guess this is an algorithm that doesn't have a very balanced workload distribution, because in the beginning, say you have 8 processors, you divide into 4 groups. So only 4 processors are busy performing the blending. In the next stage, you only have 2 groups. So only 2 processors are busy. And then in the final stage, only 1 processor is busy. So as you can see, at every stage, you reduce the number of processors that are going to participate blending to half of it. So the workload becomes more and more uneven. To solve the parallel load balancing problem, the question now is, how can we keep everybody busy all the time? I'm going to propose another solution that will make everybody busy at all stages. Again, assuming we have A partial images in the beginning, and we need to composite according to the visibility order, that is A is the frontmost and H is the backmost. So how do we keep everybody busy? What we can do is, we're still going to divide the A images into 4 groups. Instead of one processor send the entire image to the other processor for blending, we divide the image into 2 halves, say left and the right halves. And then within the group, each processor will send 1 half to its partner for blending. For example, if you focus on A and B, the processor that originally hold B image will send the left side to the processor that have A. And similarly, a processor that holds the image A is going to send the right half to the processor that holds image B. This will make both processors busy, because processor that holds A is going to blend the left half of the 2 images, and processor that originally holds B is going to blend the right half of the 2 partial images. And for the group that has C and D, and E and F, and G and H, they will all do the same thing. So this is one way to make 8 processors simultaneously all busy working on blending some of the pixels. So the result is that the first processor is going to hold the left side of A and B blended result. The second processor is going to hold the right side of images A and B together. Similarly, for the second group, one processor is going to hold the left side of C and D partial images blended together. And the other processor will hold the right side of the partial images blended from C and D. So now, after this stage, each of the processor will hold half of the images computed from blending 2 partial images. So what do we do next? As you can see here, what we need to do next is to blend the left half of A and B on top of left half of C and D. And similarly, we need to blend the right half A and B on top of right half C and D. This is because A and B blended result is immediately in front of C and D result. To proceed to the next stage, what we can do is we can break the half image into 2 quarters, and then the processor that holds A and B left half is going to work with the processor that holds C and D left half. Those 2 processors, they are going to break the image into 2 halves and then send half of image to the other processor for blending. Precisely, the processor that holds A and B left is going to send the bottom half of this partial image he has to the other processor that holds C and D. And similarly, the processor that holds left side of C and D is going to send the top half of the partial image to the processor that holds A and B left half. So So now we further divide the work to half, and then A and BL and then C and DL is going to be blend together. Each of the processors that have those two images will be responsible for blending a quarter of the total image. So we are going to perform the same thing between the processor that holds A and B write and then C and D write. Again, those two processors is going to exchange half of what they have and then perform blending. So this will result in 8 partial images, and each of the partial image is a quarter of the original size. As you look at the labels here, you can realize that the upper left corner, for example, we already blend all the corresponding portion from image ABCD. And what we need to do now is to blend the upper left corner together from ABCD and the EFGH. One process is holding the upper left corner of ABCD blend result, and one process is holding the upper left corner of EFGH blend result. So this is what we will do. We will divide the quad image further into 1/8 image, and then we are going to find the corresponding 1/8 of image and blend together. For example, we are going to blend ABCD and the corresponding part in the original EFGH. Similarly, we are going to blend the corresponding parts from ABCDRB to over here, the half of the quarter image at the same location in the image plane, that is EFGHRB, and they are going to exchange the half of the images from these quarter images and blend together. So finally, when all this is done, because we have 8 processors, so each of the processors is going to hold 1/8 of the final blending result. If you look at the image here, we have labeled A, B, C, D, E, F, G, H, which means we have already complete blending of the images that originally assigned to each of the 8 processors. So now I just finished the principle of this parallel image compositing algorithm based on this recursive halving strategy. Now, let's look at the volume rendering algorithm. A volume data is a 3-dimensional array. How are we going to apply the principle I just mentioned to perform parallel volume rendering and also to blend or composite all the sub-images together in parallel? And again, the goal is to make sure everybody is equally busy in performing the rendering and also in performing the image compositing. So let's look at the diagram at the bottom. Starting from the original 3-dimensional data, based on the number of the processors you have, you're going to divide the data into contiguous subblocks. In the example here, I have 8 processors, so I divide this into 8 pieces and assign it to PE1 to PE8. What we are going to do is, in the first stage of the parallel volume rendering, each processor is going to perform their local rendering. That is, they are going to render the data assigned to them and produce one partial image from the data. So what we are going to do is we are going to base on our view angle to blend them together. That is, we need to blend the front images on top of the back images. So let's look at the data partitioning first. Like I say, we need to divide the data into subblocks and give one subblock to each processor. Here, I'm assuming we are using this contiguous block partitioning scheme. More specific, I'm going to talk about how do we use KD tree or KD partitioning to subdivide data. The idea of KD partitioning is to subdivide data in alternating dimensions. Given a 3-dimensional data, you're going to divide the x dimension in half. For the resulting 2 subblocks, you're going to divide them in the dimension of y, and then you divide the z, and you go back to divide the x and y and z recursively. So this is how it works. Starting from the original data, I will first of all divide x dimension, and for the resulting 2 pieces, each of them I'm going to divide along the y dimension. And now is z dimension's turn, so I will further divide to z. Assuming I only have 8 processors, and I will stop here because I already have 8 blocks and I will give 1 for each processor. But if you have more processors, you need to continue to subdivide. Now, I can even encode the location of the partition based on the order they're being subdivided. For example, the first bit is going to correspond to x subdivision. The lower half of x, I'm going to give the bit of 0, and upper half of x, I'm going to give 1. Now, for the second bit, I'm going to record the y. And again, the lower half of the y, I'm going to assign a bit 0, and the upper half of the y, I'm going to give bit value of 1. So this is actually why the lower left corner has bit string of 0, 0, and to its right it has bit string of 1, 0, which means 1, 0 means along the x dimension, this block is at the upper half, and but along the y dimension, this block is at lower half. And the third bit is going to be used to record the z partition. And again, the lower half of z is going to receive a value of 0, and the upper half of the z is going to receive a value of 1. After we partition and distribute the data to each of the processors, the processor is going to perform rendering according to the current view direction and generate images. Now the next question is, how do we know the visibility order? That is, how do we know the order that we're going to use to composite those images together? So this can be done actually quite easily. Assuming your view direction is XYZ, you can determine the front and back relationship between the data block by looking at the sign of X and Y and Z component. Let's take an X as an example. If you find the x value of your view direction is greater than 0, then you know the ray is going from lower half of the x coordinates to the upper half of the x coordinates. In other words, the lower half of the blocks in the x direction is going to be in front of the upper half of the blocks. Similarly, you can determine the visibility order along the y direction by looking at the sign of the y component in the view direction vector. If y is greater than 0, then you know the lower half of the blocks in y will be in front of the upper half. This can be done by checking the value in your bit, because like I said previously, in the example, the second bit represents the y location, that is either the lower half or upper half. So you can check the second bit and you know who is the lower half, who is upper half, and based on the value of the y component, you can decide which blocks are going to be in front of the other blocks. Similarly, you can check the sign of the z component to determine the visibility order along the z direction. So now, based on that principle, let's look at how do we perform compositing. In our example here, we have 8 processors and we divide them into 8 blocks, and each block is rendered by a processor and we are going to generate images. Here I label the image by their corresponding data blocks. So I have 000 and 001 and so on and so forth to 111 because we have 8 data blocks. And by looking at the view direction vector, for any 2 blocks, you're going to know which is in front of which. Now let me show you how do we perform image compositing using the algorithm I just presented. First of all, you're going to look at the rightmost bit, and you're going to perform this binary compositing with your neighbor. And one of the block has bit value 0, one of the block has bit value 1. And like I said, you can look at the value of the view direction to determine which is in front of which. To balance the workload, you partition the image into 2 halves, exchange the halves, and then perform partitioning. In the second pass, you are going to composite with the corresponding process by looking at the second bit, and you subdivide image, exchange, and composite. And the last pass of the compositing, you look at the leftmost bit. Remember, this is because we have an example of 8 processors and 8 block, and you find out your corresponding processor, exchange, and composite. So this is the final result. So now let's briefly look at the cost of this algorithm. Given n processors, the number of stages is going to be log n. And at each stage, each processor is going to send one message to the corresponding processor that will perform composite together. So each stage we're going to have n messages. So the total number of messages is going to be n times log n. About the size of message, every pass we have n divided by 2 pairs. And within the pair, in the first pass, we are going to send a total of 1 image. Why this is true? Because imagine each of the processor pair is going to send half of the image. So the total size of image within the pair is 1 image. Now, the second pass, because every processor only holds half of the image, so within the processor pair, the total size of image that is going to be transmitted from both of the processor is going to be half of image. And the third pass is going to be 1/4 of image within the processor pair. And if you keep going until the last pass, And because we have log n passes, so the last pass we're going to have 1 over 2 to the log n minus 1 image within the process pair being sent. So if you do some calculation, you're going to find out the total is n minus 1 images. About the parallel efficiency, as you can see, because at every stage, all the processors are busy, so in terms of computational load balancing, it is the best. And also they are perform the same amount of work, that is composite the same size of image as everybody else. So this is the famous binary swap algorithm used for parallel bind rendering. Okay, so this concludes our topic of parallel bind rendering and parallel image compositing.